Okay, you remember last time we started with a new topic, which is the last topic to be covered this semester, which is differential equations. And I mentioned that we can solve differential equation using different methods. Mainly, if I want to classify, I will say there is numerical method and there is analytical method. Numerical method to be discussed in level 3. But now we discuss the analytical methods. These analytical methods could be classified into direct, separable, exact, linear, Bernoulli. Okay, so we will discuss these methods in the next few weeks.
Doctor,
Yes,
can you share the screen, please?
I'm sharing. Is it not? You can see it?
I can't.
You can't. Okay, let me. I suppose that I share it. Let me repeat sharing again. Okay. Can you see the screen now?
Yes, doctor.
Great, great, thank you. Okay, so when we say differential equations, just 1 second. Okay, when we say differential equations, we're talking about dy equal dx over dx equal, let me say, function of x, whatever the function there to the right. This is ordinary differential equation. In the opposite side, there is partial differential equation to compare between them. Partial to be discussed, inshallah, level 2. But now, this equation is y already differentiated. What we want to do is we want to get the original y. So we will integrate, definitely. You will say, okay, let's integrate. This is what happened. We will integrate. And when we get the solution, in this way, y equals something, we call it implicit solution, explicit solution. Okay, in the opposite direction there is implicit solution. What is implicit solution? Implicit solution when y and x came together mixed, it's not y equal. Okay, example here for implicit solution, have a look. He told me that this is a solution. Which one? Implicit solution for dy over dx equal minus x over y. Implicit because y came with x together. It is not y equal. Now if I come to this function and integrate, differentiate, it will be 2x and here 2y dy over dx, and here the 25 differentiation for it will be 0. Rearrange, we go with this function. Yeah, this is correct. This is correct. This function is implicit solution of dy over dx equal minus x over y. Now, if we plotted here the implicit, we will get the all options from different direction. But if I take x squared to the other side, will be minus x squared, and take square root in this way, it will be plus minus. Okay, so y will be now explicit. As you can see here, we will have y1, we will have y2. We can sketch them. Now it's y equals something. Still, I'm introducing the topic, the terminology. And by the way, just don't forget that when we integrate, what we will have constant, which is called arbitrary integration, arbitrary constant. This constant, which is most of the time we call it c. If we don't have initial condition or boundary condition, we cannot find it. But if we have initial condition, we can substitute to find it. And when we find it, it will be specific. Example of this, have a look. If I have this function as example, x equal c1 cosine 40, it is already integrated and I got this result. But see c1 here. C1 here tell me that there is infinite number of output for this x. Why? Because use C1, you get different curve. You see here as example C for this function. When I integrate, if it is not known for me, I will have different curve. If I select C1 or 7 or million or 1000 -7, whatever it is, you will have different curves. To find the or select the right curve, you need to have initial condition, as I mentioned. Initial condition, when it's given to you, just to find the constant C. Another terminology is the homogeneity. Homogeneous, when we say the equation homogeneous. Homogeneous in front of non-homogeneous, we are going to deal with them and solve many problems in the next few weeks. It's talking about that we have all items to the right. I will give example. See this equation. dv, my variable is v now, not y, over dt equal g. This is first order differential equation because it's derivative once. It is linear because there is nothing to make it non-linear. It is non-homogeneous. Why? Because g here to the right supposed to be 0. Since it is g here a function, then it is non-homogeneous. See here, he gave me initial condition. He told me at t0 v will have a value. So this is initial value problem. Another example. This equation, this differential equation here, see how many times we differentiate? 2. So this is second order differential equation. And also it is linear. There is no problem with its linearity. CW to the right hand side, this is non-homogeneous. See here, he gave me boundary condition. When m is when x is 0 and when x is 1, I have different value for m. Another example. Here, as you can see here, I differentiate twice. So this is second order differential equation. See to the right, we have 0. This is homogeneous. And there is no problem with linearity. No, there is a problem. Have a look. This is theta. My variable here is theta. And since theta came with sine, so it is nonlinear. If it is only theta, there is no problem. But since there is sine, it becomes nonlinear. It means curve at the end, not straight line. And because of this 0, you can see here, what we have homogeneous. And here he gave me initial condition for theta and for d theta. He gave me initial condition. Last one, I want you to tell me. Now this equation, the last one, you tell me. Is it first order or second order differential equation? Excellent, second order. Is it linear or non-linear? Why non-linear? Anybody? Okay, let me explain it. See my variable here, theta. My variable here, theta. Now theta came alone, no problem. Omega squared doesn't matter. It's not my problem now. Omega is a constant. Theta is my variable. Is there anything, square as example, square root, sine, ln, exponential? Nothing. It's only theta. So this is, let me say, linear. Now, if 0 to the right, what we say, this is homogeneous or non-homogeneous? What do you think?
Homogeneous.
Excellent. And he told me that there is initial condition for theta, for d theta, then I will say this is initial value problem. As I mentioned, we have numerical method or analytical method to be used in solving ordinary differential equation. We will focus on analytical, this one to be taken in level third level. And there are many methods. One of them is the direct, from the name. Separable, also their names give impression about the method itself. Exact, linear, Bernoulli. Today we will talk only about separable, because direct I will go through it very fast because there is no problem with direct. Example, if you are given as example, this is a practical example, the velocity of a car that is accelerating from rest at 3 meters per second. So dv over dt, talking about the acceleration, this is velocity, this is t, equal acceleration. This is the definition from secondary school, equal 3, he told me. Solve it, very simple. When I integrate here, it will give, with respect to t, okay, with respect to t, it will say that velocity equal 3t plus constant. For that, we call it direct integration. Okay. Now, if I am given initial condition, let's say he told me that the speed will be 0 at time 0, then I will substitute time 0, speed 0 here. Here 0, 0 would mean that C0. I back to substitute 0 for C, and this is the final answer. Direct, very simple. Okay, another example. Y dash equals sine. We integrate sine, we integrate y and sine. Y dash will be y and sine will be minus cosine. Very simple with a constant. Integration this one, this differential equation. This will be 3x to the power 3 over 3 minus 6x to the power 2 over 2 plus 5x. Direct. So here I gave you some exercises to enjoy at the weekend, solving them, practice more on direct, which is, let me say, very simple and separable. More problems here, more problems here. You see this one? It is direct. Just integrate. This one will be x to the power 3 over 3. This one will be x to the power 4 over 4. Done. Integrating this one. Okay? X to the power 3, it will be x to the power 4 over 4. 3x to the power 2 over 2. Now, if he gave you initial condition here, you see, I integrated. You see, x over 4, the power 4 over 4, x to the power 2 over 2, plus c. If he gave me initial condition, he told me here that x equals 7, then y equals 4. So I will say, okay, 4, which is y, equal, I will substitute for each x by 7. I do the math, I got c. So the initial condition given to you just to find the constant c. And more problems here, as you can see, more problems. X squared plus square root x. This need to be converted into x to the power 1 over 2, similar to this. And then I integrate x squared plus 1 to the power 3 over 3, x to the power 1 over 2 plus 2 over 2 over the new power, as you learn in semester 1, plus c, and so on. I will let's have a look at this one. When you integrate in the previous examples, it is direct integration. I mean, the method is direct for solving differential equations, but the integration is direct. I mean, I give you x squared, you integrate it, it will be x to the power 3 over 3. But sometimes you are given in this way. Don't forget, I revised it last session. I revised the methods you use for integration by substitution, algebraic substitution, trigonometric methods, the table, if you remember, integration by parts, partial fractions. We discussed them. Now, here you are given, you see here, this is x t squared. So I will go to the assumption, u equal t squared, then du equal to t dt. Very simple. Now, I will convert this function, this equation, from function of t into function of u. I will say, okay, this one, for t, I can find because t squared equal u. Okay, and exponential t squared. So I substitute, I have here everything, substitute and convert my function, it becomes this way. Now you tell me, integration exponential minus u du, what it give me? Minus exponential minus u. Directly, this is standard, as you can see here. Plus c. That's the end, finish? No, we need to convert u back into t. You see here, u is t squared. I convert it back. If I am given initial condition, I use it to find the constant c here. As you can see here, I have initial condition tell me that at t0, y 1 over 2. So I come to substitute here y over 2, 1 over 2 for y, for t here to be 0, and solve to find c. Very simple. This is direct. Now last point here. Okay, I want you to start focusing in the next 2-3 slides. I will finish, I will conclude. Because this is the first important method. We have direct, it's very simple as I mentioned, separable, exact, linear, Bernoulli. today, the remaining time is for separable. Have a look. Separable from the name, if you see here, dy over dx, it's equal to expression containing x and y. The name separable, it means I will separate between x and y. X will be on one side, y will be on the other side. So I want to make this y square to the other side. I will divide by y square, as you know. Okay. So when I divide here by y square here, 1 over y square, this one cancelled. It's already here. And dx here, I wanted to take it to the other side. I will multiply the equation by dx and dx. Dx here cancel. This is how to like the equation, the new equation. Now you can see y on one side, x on the other side. Now I can integrate here and here. As you can see, definitely I need to take this y square over there. It will be y to the power minus 2. Now put integration here and here. Now integration of x with respect to x, it will be x to the power 2 over 2. And this one, it will be x to the power minus 2 plus 1 over minus 2 plus 1. As you can see. So this is what I got. Definitely when I integrate, I need to add constant. Okay. Now I added constant here. I call it C1. And constant here, I added C2. I will take C1 to the other side, will be minus C1. Both together, they will give C. I mean, C will be C1, C2 minus C1, one constant in this way. Okay. I want to make it y equals something. So I will rotate my equation. Okay, reciprocal. And multiply by minus. Now y equal this expression. Now the name separable means separate x from y. You need to focus on this. Separable meaning separate x from y. Now the constant given to us will create infinite number of curves, infinite number of functions. As example, this is dy over dx equal xy. Very simple, cross multiply. We are here, we integrate, we have y square and x square, you know, y square over 2, x square over 2 plus c, 1 multiply by 2, it will be in this way. But since I don't have value for c, I will have infinite number of formula. Okay, infinite numbers of curve, as you can see here. We need to specify c. Usually, initial condition given to you to do this. Now, see the previous function here. I just solved. He told me when x is 0, y is 2. So I will come here, 2 square equal x0, 0 square plus c, as you can see here. Solve it, we go to c equal 4. Then I will say, okay, then y square equal x square plus 4. Very simple. Another example. You are given this equation, dy over dx equal 2x between two brackets 1 plus y square exponential x square. Just a minute. This item contain y and other items contain x only. So if I divide by this item, the whole equation, then it mean there is only x on the right hand side. You see here? I divided. Now what is left? This item and this item, as you can see here. While also I multiply by dx, so this dx came here. Now see this expression, is there any y? No, there is no y. I can integrate now. Is there any x here? No, there is no x, only y. I can integrate now. The remaining is merit of integration. We discussed integration in last semester and I revised it last session. Now how we integrate? For this part, I remember there is a formula in the trigonometric substitution table, the 12 rules, say that if my function in this way, its integration is this part. So great, this one done. Here I have x squared and I have x. Oh, I need to solve it by algebraic substitution. I will assume x squared here to be u and convert the whole expression here into function of u. It means differentiate will be du equal 2x dx. Okay, you see here this 2x dx will be du and exponential x squared will be exponential u, as you can see here. Now this part directly integrated, it will be exponential u. Then if I back to substitute u by x squared, then I have this expression, as you can see here. Take c1 to the other side, it will be c. For that, usually we directly write c. 1c, that's it, done. Okay, now I will take here as example tan inverse. I will take tan for the whole equation. So tan inverse going with tan, what is left? Y. As you can see here. To get the explicit. Now this is explicit, y equal expression. Now one more issue here. If I differentiate y here with respect to x, I suppose to back to the original function here. If you want to check your solution, do it in this way. Last example. See this dy over dx equal y over x plus 1. Now when I want to separate, I have difficulty. Why? Because there is a plus between this expression. It could be any number, it could be anything. Now when plus or minus came between x and y together with something else, variable or number, or we cannot do the separable method directly. We need to have assumption. How? Have a look. Close your, please make sure to close your monitor. Okay. Now have a look. Y, I will assume y equal vx. V is another variable. It's like substitution, algebraic substitution. Then if I want to differentiate this dy over dx, it will be v dx over dx plus x dv over dx, right? In this way. I equated to this expression. Don't forget y is vx, okay? Now I will take v to the other side. It will be minus v. Don't forget x gone with x. V plus 1 minus v gone with v, as you can see here. Okay? Now cross multiply, we will have dv equal dx over x. Integrate, it will give ln x plus constant. But I don't want v, I want y. So I back from here, v equal y over x. So I substitute multiply by x, I got this expression. So the only idea here is when I have plus minus, I need to go for assumption. I assume this one here, and then I go for function of x and v. It will become separable directly, solve it, and return back to y. Now I will stop here. Do you have any question before I have a few points to discuss with you? Okay. Just a minute. I have a few points to highlight. Just 1 second.